In this video, we are going to discuss about the thermal engineering subject. Topic is Brayton cycle. Prepared and presented by M. Rajkumar, Assistant Professor, Department of Mechanical Engineering, Rohini College of Engineering and Technology. Brayton cycle. Brayton cycle or Joule cycle. Brayton cycle is a gas power cycle on which an ideal gas turbine works. It consists of an adiabatic compression, constant pressure heat addition, adiabatic expansion, and constant pressure heat rejection. The ratio of pressure after and before adiabatic compression is called as pressure ratio. This is the schematic representation of an as standard Brayton cycle. It consists of compressor, combustion chamber, turbine, and cooler. This is a schematic representation of air blender Brayton cycle. In the compressor means the inlet condition is 1 and exit condition 2, and combustion chamber inlet condition 2 and exit condition 3, turbine inlet condition 3 and exit 4, and cooler inlet condition 4 and exit condition is 1. This is the Brayton cycle schematic diagram. Then Brayton cycle PV and TS diagram. You can see this 1 to 2, 2 to 3 and 3 to 4. This is the PV and TS diagram. First 1 to 2 represent the isentropic compression, 2 to 3 represent the constant pressure energy addition, that is heat addition, 3 to 4 isentropic expansion, then 4 to 1 constant pressure heat rejection. This is the expression for the PV diagram. Next, we are going to see the energy added, that is heat supply equal to mCp into T3 minus T2. Then heat rejection Q2 equal to mCp into T4 minus T1. That is the final temperature minus initial temperature. We know the efficiency formula eta equal to work done divided by heat supply. Work done means heat supply minus heat rejection. We know all the value from the above equation. Substitute the Q1 and Q2 value and Q1 value. In this efficiency equation, we get 1 minus T4 minus T1 divided by T3 minus T2. From this simplification from this eta equation, we get 1 minus T1 into, we know take the T1 value common outside for common value, that is T1 equal to T4 divided by T1 minus 1 divided by T1 into, that is eta equal to 1 minus T1 into T4 divided by T1 minus 1 divided by T2 into T3 minus divided by T2 minus 1. The pressure ratio of the Brayton cycle, that is RP. RP is represent the value RP is a pressure ratio, that is RP equal to P2 by P1. The process of 1 to 2 and 3 to 4 are isentropy, hence P3 by P4 equal to P2 by P1. So we know the PVT relation formula, T2 by T1 equal to P2 by P1 the whole raised to gamma minus 1 by gamma, and T3 by T4 equal to P3 by P4 the whole raised to gamma minus 1 by gamma. So this we can simplify this value T2 by the constant pressure. So we can strike out the pressure values, then T2 by T1 equal to T3 by T4 or T4 by T1 equal to T3 by T2. Simplify this value, substitute this equation, eta equation, we get that eta equal to 1 minus T1 by T2. So we can value, replace the temperature into pressure, so that we get the value 1 minus P1 by P2 the whole raised to gamma minus 1. So efficiency equal to 1 minus 1 by RP. We know the RP equal to P2 by P1. Here we have the P1 by P2. So inversely we can substitute the RP value. So 1 by RP the whole raised to gamma minus 1 gamma. This is the efficiency formula for the Brayton cycle or Joule cycle. Next, we are going to see the Brayton cycle problems. So Brayton cycle, the air enters the compressor at 1 bar and 25 degree. The pressure of the air leaving the compressor is 3 bar and temperature at turbine inlet is 650 degrees centigrade. Determine per kg of air. First one, cycle efficiency. Second one, heat supply to the air. Third one, work input. Fourth one, heat rejection in the cooler and temperature of air leaving the turbine. First, you should draw the schematic diagram of the Brayton cycle. Then only you can take the data correctly. Okay. So given data, P1 equal to 1 bar, T1 equal to 25 degrees, convert into Kelvin, plus T3 value equal to 650 degrees centigrade, convert into Kelvin, and P2 equal to 3 bar. So consider the process 1 to 2 adiabatic compression. So we know the formula T2 by T1 equal to P2 by P, the whole raised to gamma minus 1 gamma. So we know the value of T1, P2, P1. So from this substitute all the value in the equation. So we get the value T2 equal to temperature value we get from this formula. So then 3 to 4 adiabatic process. So T4 by T3 equal to P4 by P3 the whole raised to gamma minus 1. So we know all the values, substitute all the value, T3 value, P4, P3 gamma value. So substitute all the value in the equation, we get the value T4 equal to 674.3 Kelvin. This T4 temperature they are asking the question. Then the as standard efficiency eta equal to 1 minus 1 by Rp the whole raised to gamma minus 1 by gamma. So we know the value of Rp value, gamma value. So substitute all the value in the equation, efficiency equation, we get the value of efficiency. Then heat supply we know formula. Qs equal to Cp into T3 minus T1. The M value equal to per kg. So M value equal to 1. So we know the value of Cp standard value 1.005. We know value T3 value, T2 value. Substitute all the value in this equation. We get the value of Qs, that is heat supply. Then heat rejection equal to Qr equal to Cp into T4 minus T1. We know all the value Cp is T4, T1. So substitute all the value in the equation. We get the value Qr. Then compressor work. WC equal to Cp into T2 minus T1. So we know all the sub value T1, T2, Cp. So substitute these all the value in the equation. We get the compressor work WT equal to 110.55 kJ per kilogram. Similarly for expander WE, that is C equal to Cp into T3 minus T4. So substitute T3, T4 value. We get final for our expansions. Work expansions equal to 140.288 kJ per kilogram. Then temperature of air leaving the turbine equal to 673.4 Kelvin. Thank you.